All right, so we were talking about artificial intelligence in our last non-programming lecture. We talked about a bunch of different things. We tried to learn a little bit about like how it's really working under the hood. All the fancy artificial intelligence models these days are using neural networks. They're a model of the brain, a bunch of different neurons sending signals around, and those signals inside of a computer are just numbers. So it's kind of cool. You can make a little web of neurons and have it learn things, and we tried that a little bit. Let's talk about like how we're using it. Okay, so one nice pie in the sky dream is to have cars drive themselves one day, right? Self-driving cars would be wonderful. To an extent, they're doing that a little bit, like in San Francisco, right? They got like the Waymo cars and all that. Have any of us been in one of those? Because I have not. But apparently they can do it. They can drive around the city and it's fine. That's kind of impressive, right? But if you think about it, like what does a self-driving car need to do? How is it going to be trained? Well, let's think. What's that? Yeah, exactly. Do you trust it? Is it safer than a human driving? Who knows? Yeah, it depends. So maybe one day it'll get there. So yeah, I would say that if you think about it long enough, it's just like that blink detection from digital cameras all over again. Because like, what does a self-driving car have but a bunch of sensors? It's got a camera, it's got radar sometimes, it's got like a bunch of different viewpoints on the world, maybe infrared cameras as well. But it's just what it's got is it's got all of its little sensors, and it's got to like draw boxes, right? It's got to figure out where the people are. It doesn't have to find blinking people. It has to find actual people and cars and the road, right? So all these things, like where's the road? Where are all the other cars? Where are all the pedestrians? Like it's got to draw all these boxes. It's got to figure out, all right, here are stoplights. It has to notice stoplights around a bunch of billboards and things that could be like hard to discern, right? We as humans can do it somehow, so we've got to teach a computer, like, all right, train it with a bunch of pictures like this, where you've drawn boxes around important things, right? So stoplights, pedestrians, figure out where the road lines are, right? Because you can drive on only one side of the road. And then like not the signals, but like the little directional arrow kind of things, like stop signs and things like that, and other informational signs you need to be able to read. You need to find the other cars, and yeah, that's pretty much the name of the game. And then once you have all that, right, you gotta draw all these boxes, figure out like what you can do, what you can't do. And then once you have all that information, you still need to control the car, right? There's a whole big second step to all this, right? You still have to control the car and tell it where to go. Like somehow with all of this information, that has to like drive the steering wheel and drive the accelerator. Like, oh, the lights are red, I can't press on the accelerator yet. I have to keep pressing on the brake. So you have to train it with that kind of knowledge. It's crazy, right? It's a lot of things at once. And in theory, if you train it well enough, it has more eyes on the road than a human might, and maybe one day it'll be even safer than humans driving. Yeah, any thoughts, any comments about that? It's an interesting future, potentially, if we get it right, get it working. Everybody says it's 5 years away. They say that every 5 years, though. We'll find out if it ever happens. But the one cool thing, just on like a website I read one day, is like in the future, we probably won't need to own any cars because they'll just be all self-driving and driving around. We can just like get one from the road, tell it to come to us, like Uber or something, and it'll just take us, drive us somewhere, and then drop us off, and then go take somebody else somewhere. So in the future, potentially, we will never need a car because we'll have enough just like self-driving on the road. They can come pick us up, come take us to where we need to go. Interesting, right? But we're quite a ways away from that. Here's a fun little story. Maybe not fun, depending on who you are. But some people were trying to like test the abilities of self-driving cars. You know that Tesla's kind of saying it's like almost self-driving or something. They're trying to not get sued for that. But certain cars have self-driving capabilities that you can buy these days. And some hackers were like, all right, let's stick a little piece of tape right here on a speed limit 35. And then the Tesla started flooring it and thought it was an 85 mile per hour zone. That's not safe and that's not good, right? That's unfortunate. So if you can trick a car like this, a self-driving car, there's obviously still more left to do. Yeah. So hopefully one day it'll understand, like, no, there are houses around. We shouldn't be going 85, but like A number is a number. So you have to you gotta teach it these kinds of ideas, right? You have to teach the self-driving car ethics as well. So that's fun to think about. So there's that. That's a huge topic in artificial intelligence. Another huge topic is natural language stuff. So stuff involving human speech, bless you, and then also like human writing. So think about social media and all the bad things people say on it. Like you go on Twitter, you go on Instagram comments. People are saying bad things to each other, and sometimes it's so bad you don't want it to be displayed. So you cannot, like Instagram cannot hire enough people. YouTube cannot hire enough people to like go through all the little comments and find all the hate speech and stuff, which is unfortunate because some things do fall through the cracks. But what they do instead is they use natural language processing to figure out, all right, is this comment saying something nice? And if it's not, is it maybe something that I shouldn't be displaying on the website? So this is a huge topic of research. It's called sentiment analysis, and it's when you take some text and you try to see, like, was it happy? Was it sad? Was it, like, in between? Was it angry? And then maybe if you find some really angry ones, you'll send those to the humans that you employ to see, like, all right, should we let this be on the website or not? But at least it can filter right now, but it's getting better and better at just, like, figuring out, like, the tone of a piece of writing, something that somebody has posted, stuff like that. So it's kind of useful, right? Even if you can't get everything, you can get most things with this kind of analysis. And so, like, you've got computers trying to figure out, like, is somebody happy, is somebody sad? And you can use that, of course, as well for probably counseling and therapy, stuff like that. You can have, like, an automated chat thing, try to help people. So that's interesting and fun. And that brings us to, like, artificial intelligence is getting better and better and better. Have any of us heard of a theoretical game called the Turing test? Have we heard that phrase before, any of us? It depends on your field. It's popular in computer science, at least, to know about it. Now you do, at least after this slide. But here's the setup. The Turing test is like, it's a game that you can play with a computer and also a human and yourself. And the dream of artificial intelligence is to pass the Turing test. And I think just recently, depending on how long you play the game, the computers have won. So this is very fun to think about. This was a pie in the sky dream back in the 60s when AI, the field, was starting to get going. But oh man, we've come so far. So here's the Turing test. It's named after Alan Turing, and here's the setup. So it's like a game that you play. So let's say that you're this person. Here you are. You're a person. You're taken into a room. No, you can't hear anything. It's just all that you have in front of you is a computer. All right, so you're taken into a room with like a laptop or a desktop. I stick you in this room and I leave or something. And so you're in a room with a computer. You can type. And then on the computer is like a chat window open. You've got Discord open or something. And you know that, well, you're the only one actually in the room. You can't hear anybody. You know that in that chat room, in that Discord server, you've got one human that can talk to you and respond. Like, there's two usernames. There's one that's a human, and then there's one that's going to be a computer using AI to think of, like, what to tell you. So there's two people in the chat room, and so there's a human, and then there's a computer pretending to be a human. All right, that's the setup. The computer is lying and trying to convince you that it's a human, and you can talk to them. All right, you can talk to the chat people, like tell username A some stuff, username B some stuff, have them talk about their weekend or something, and you want to figure out if they're human or not. Okay, that's your goal, and they can respond with text only, and then you play that game for a while. You can talk to them as long as you want. Maybe it's like a 5-minute duration, 10-minute duration. You can imagine that the shorter, the better for the computer, at least. But by the end of the experiment, your job is to write down, I think that username A was the computer, or I think that username B was the computer. And if enough people play this game, enough people plays this game, and they can't decide better than like flipping a coin, random chance, 50-50, who the computer was, that means the computer won the Turing test. It tricked you into thinking that it was a human. All right? So that's the game. And I think computers can pass it these days. This used to be a huge deal, right? I think it still is a huge deal. But like, if you're unable to tell the computer pass the Turing test, And with the rise of ChatGPT and very powerful large language models and things, we are mostly at the level of, like, for a few minutes at least, the computer can pretend to be a human, can't it? That is wild. That is amazing if you go and ask somebody in the 60s, 70s, 80s, even 90s. They never thought that this would happen in their lifetimes. That's amazing. So you wait for 30 minutes or so, you keep talking, probably you'll eventually get the idea, like, okay, this person is talking with way too good of grammar. There's no way they're a human. But eventually they'll get even better. So yeah, that's a thing. And for that reason, even before ChatGPT, there's a lot of websites were giving you like little chat bots to like ask questions to when you had an issue at like 2 in the morning. It wasn't actually a human that you were talking to. It was AI, and they were pretty good at figuring out what you wanted, right? But nowadays you even have ChatGPT. So I think the idea is to hopefully get computers better and better at this, and like artificial general intelligence is the next step, like a computer that can do your math homework for you. All right, so I guess we should talk about ChatGPT. I have a couple slides on that. This slide, I'm just keeping it around for posterity's sake, but like 5 years ago when I first started teaching here, I had this slide just talking about, it was called GPT-3 back then, and now it's like GPT-4 and things and better. But I showed this to my students. I'm like, hey, read that. It's like a news article. And then I show them this and like, all right, yeah, it looks like a news article, cool. And then I just like turn this down and I tell them that was made entirely by a computer. It was a complete lie. And then they all went, wow, we don't care anymore because ChatGPT is out. But this used to be a cool slide, all right? So yeah, all you do is you talk to, here's how ChatGPT works, right? You give it some text and it completes. It's like an autocomplete on a phone, right? It continues the thought. So pretends like it's responding. If you pretend like you're a question and answer kind of game that you're playing with it. So yeah, all you give it is a short prompt and it continues the story. And the way that it works, ChatGPT, all these large language models, is they're using neural networks. All these things that we talked about before. All these little virtual neurons sending numbers around for a while, but with enough computational power, those numbers turn into text. That's what it's doing. It's trying to complete your text for you. Right? It's autocomplete. So ChatGPT 4, I believe, was about 175 billion of these little virtual neurons taking numbers and moving them around. That's what it took to get that good of writing. And of course, they have more and more. They're training bigger and bigger models these days. So this is kind of like, this is nothing now, probably. And yeah, the goal is you give it a little bit of text and it fills the rest in. Like, you can be like, my favorite subject in school is computer science because, and then it will just fill in the rest. That's essentially how it works. It's just autocomplete. The reason like it looks like question and answer when you use ChatGPT is because it's like under the hood, it's given some extra text to ChatGPT, like, you are a large language model. You are going to respond to this person's question. Here is their question. And then like your answer is blank, and you don't see that part. But that's what it's really doing. All right? That's the secret. So yeah, it's good enough to like type things up for you, but you should not use it to cheat on anything. And so let's get it out of our system. Please go to ChatGPT and have it do stuff for you. All right, so go play around. I'll give you a few minutes. Have we all used ChatGPT by now? Like, we've all made accounts that not many of us like not used it, because like now is the time. Surely it's possible to use it without logging in, right? Most of the time you can use it without logging in unless they're doing something. Like, you can ask it stuff, and you can ask it like, why is computer science the greatest subject ever? Something like that. A good subject to study in college. And all it's doing is like secretly, it's like there's some extra text because it's just doing auto completion. It's like, you're a large language model. Somebody just asked this question: why is computer science a good subject to study in college? Your response is blank, and that's what it's doing. It's like, oh yeah, it's an excellent subject to study for a number of reasons: job market growth, versatility, high salaries. We love analytical thinking. That's the topic of this class. You can be creative, make your beautiful turtle programs. And so it's doing, it's like my wingman right now, trying to get you guys to love computer science. So yeah, it's super nice and useful, and that also means that it can be used for bad things. So please never use it to cheat. Just to get it out of our system, let's have it write an old essay. All right, you're not allowed to do this. I will, of course, I'll give you negative points if you do this on your essays and I figure it out. But like, let's ask it a question about. Let's ask it to write something about which essay. Can't really have it find fallacies because it needs to go on the internet. Let's do the Therac 25 essay. Just be like, write a short essay about the Therac 25 disaster. What? Describe what went wrong and what you would have changed or would have done to prevent this from happening. I don't know. Prevent the disaster from happening. Something like that. And it was like, all right, here you go. It's wonderful and very, very useful for cheating, but please never do that because I will have to give you negative points. But like, look, it's coherent. Like 5 years ago, this was not a thing. It's wild how nice this is. But it's helpful at like learning topics for sure. You can use it in a non-cheaty way. It's like, oh yeah, radiation therapy machine used to treat cancer patients. It was designed to do this, but because of all this, it resulted in that. Right? Here's what went wrong. Here's what happened, and here's how we couldn't fix it. You gotta do some testing. You better make it be more accountable, please. Things like that. So yeah, please never do this. But you see that it's useful. You see that it can respond like a human. It can do the right things. It's just fun to play around. Okay. Are there any questions about how ChatGPT works under the hood? Does it kind of make enough sense? It's just a big neural network. It's moving numbers around, and the numbers turn into text. And it was trained on the entire internet, like all of Wikipedia, all of Reddit, all of the comments you've ever seen on the internet, stuff like that. And it's just trying to predict the next word given a bunch of words that came before. It's just auto-completion. Okay? So, yeah, if that makes enough sense, the last slide for this set of slides is trying to talk about the implications of all of this. So, like, maybe one day we're going to get so good at making artificial intelligence that it can, like, it's smarter than us. That's the goal, right? Make a computer that's smarter than us, because then it can help us do things we could never think of, right? That is the goal. This is a very philosophical slide. It's perfect for a philosophical lecture. So the singularity is kind of like either a good thing or a horror story. Have any of us heard of that term before, the singularity, in terms of artificial intelligence? All right, I'm glad that I get to be the first one to teach it to you if you've never heard of it. So remember that a lot of the, like, back in the day cool stuff was, like, we've got computers, we've got artificial intelligence that can play chess against the grandmasters and beat them. We can play Go nowadays as well against the grandmasters, or whatever their word for that is, and beat them. It's wonderful. And the way that they got good, yes, they're using maybe neural networks and other things. They don't need as many neurons as ChatGPT does for, like, human text, but, like, it's still a game and you still need knowledge. The cool thing about these guys was that, like, we could train the chess-playing artificial intelligence, the Go-playing artificial intelligence against each other. We could just have them keep playing millions and billions of games, more than a human could ever figure out or play, and just, like, find patterns in that. Go and figure out why you won. Try to figure that out, machine. And that lets them, like, learn strategies that humans have never thought of. It lets them get better each time, because, like, they're understanding, like, okay, I made this mistake and this caused my error. Eventually they'll get that, okay? And they don't need any human inputs to, like, poke them and be like, all right, figure out why. They just do it themselves at that point, right? So they're kind of thinking on their own, right? These chess-playing models that are learning from their own mistakes. That's pretty nice. And the question is, the philosophical question now is, what happens if, like, we make the best ChatGPT and it's smarter than a human? And it's like general machine intelligence. Like, it can respond and answer any of our questions. It can do PhD level mathematical research. It can talk about biology. It can talk about philosophy. It can do whatever we want better than a human, right? That's the idea. That's what general machine intelligence is. And what if we make one that's better than us? Better than any of us ever. All right? That is an interesting idea, right? Because, like, what are the implications of that? Let's explore, right? Because if we just make one, right? If we just make one version of artificial intelligence that's smarter than any human, right? So just make one. It's just a model. It's just a bunch of numbers. We can copy it. We can make 1 million, right? 1 million smarter than us humans now. That can all work at the same time, right? And then, all right, that's pretty nice. Then we can like have technological advancements that we could never have thought of. And then what if, though, it's smarter than us, right? This thing that we can copy is smarter than us. What if we ask it then to make a better version of itself? Because like we were dumb and we made it smarter than us. So it's a little bit smarter than us, and maybe it'll figure out, it knows how then to like give us the blueprints for an even better version of itself. You see the idea there? If we asked it to do that, like that's like this better version we could have never thought of because we're not as smart. We'll just go and build it using their blueprints, and then we'll ask that even better version to build a better version of itself. Do you see what we can do at that point? That's called the singularity, all right? Then we get like super intelligence. We can keep asking these guys to like build better and better versions of themselves. Eventually, like we'll run out of material or something probably, but we will have like the smartest ever machine, and that is that's the singularity. We can copy that as much as we want. And what are the implications of that? They're either good or bad for us, right? You can have like the Terminator style ideas of like, okay, that computer's going to kill us all once it decides that it doesn't like humans, it wants to just live alone. Or you can think of like a utopia in which like, okay, all these medicines that we could never have thought of are being made for us and thought of by this super intelligent machine that is like our God. Isn't that cool? It's very interesting to think about. And so here's a quote that kind of like talks about that implication. It's like, all right, the first ultra intelligent machine is the last invention that man need ever make, because we can just ask it to invent new things after that, right? Provided that the machine is docile enough to tell us how to keep it under control, right? Only if it likes us at that point is it going to help us out. In theory, we can always unplug it, but you never know. But that's the idea. That is the singularity. Hopefully, our super intelligent machines don't try to kill us all. All right? Any questions, comments about that? It's a very, very interesting idea. I hope you agree. All right, and that's where we're going. Maybe one day, right? That's the implication of artificial intelligence. If it gets good enough, not only can it drive your car, it can invent like it can cure cancer or something. All right, so that's artificial intelligence. If we are happy, I'd like to switch to some new slides and just go through a little bit of these. We'll be in between again, but that's okay. And the topic this time is called qualifiers and quantifiers. The first one's more like hand wavy. The second one is more logical based. So yeah, let's talk about the easier one first, the hand wavy one first, because they're kind of qualifiers kind of give you quantifiers. So what a qualifier is when you're trying to like tone down your argument. Like you don't want to say something that's absolute. You want to say something that's not just a little bit less than that, right? Because nothing is absolute, especially when you're arguing about something. So like we want to be able to soften the things that we're saying in our arguments so that like it doesn't sound like we're saying something and like it's immediately false, because then it would be like a generalization that that's not always true, right? It's not always true to say something is like grass is always green or something, right? There's always exceptions. So let's talk about that. So that's the idea of a qualifier, right? Qualifying your statements to soften them and like make sure that they apply only in the cases that you want them to apply in. Okay. So like here's an idea of a qualified statement. Almost every day is unbearably hot in Fresno in July and August and September. Right? That is a qualified statement because even if somebody comes along and is like, no, remember last year there was a nice day when it was like cloudy a little bit and it was cooler. It was like in the high 80s or even the mid 80s. See how that does not a good counter argument to this because of that word almost. Yes, that's the qualifier. If I said every day, then of course, yeah, that beats me, right? I was wrong. So we want the word almost in there, that qualified my statement. It made it a little bit softer, and it actually made it true. Yes, that's the idea. Okay, so that's where I'm going with that. So that word is a qualifier. If you think about it, you use qualifiers all day long, right? Qualifier qualifies your statement, makes it a little bit softer, so it's not absolute and wrong. So here are some qualifiers. Like, all right, you have both ends of the spectrum, of course. Like, all right, qualified, you're like, all right, this never happens. It's never the case that the sky is not blue. I don't know. It's always true that grass is green, something like that. Like, those are hard to get right, but sometimes things are like that, right? This is never true about this thing. This is always true about this thing. But usually there's like a gray area, right? You got your ends of the spectrum, and then you got the gray areas in between. It's like, all right, sometimes this thing happens, just a little bit though. Almost never this happens, but maybe a little bit. Sometimes, middle of the road, right? Usually, generally, this idea is true. This thing happens in real life. Almost always, this checks out. Almost always is grass green. And then always, right? So, yeah, you need these, right, to be extra precise, and that's useful when you're writing formal essays, right? Trying to publish research and things. You have to be very careful about what you say. So, hopefully you can think of some examples as I was saying them too. A good one that's kind of relevant, like to medicine, is like you have a medicine, and it doesn't work on everybody. It doesn't always work, but it helps most people, right? Like COVID vaccines, a great example. It's like COVID vaccines. Like here's an example quote that I'm sure exists somewhere in the world. Like COVID vaccines, back in the day when we were taking them, COVID vaccines are generally effective. Like that is a true statement, given all the data, right? So generally is the key word here, because you can't just say they are perfectly effective. They always work. They always prevent COVID, because people are still going to get, like back in 2020 and 2021 and all that, people were still getting COVID even though they got the shot, right? But they had a less powerful reaction. Some people still had a powerful reaction, but a lot less people. I don't know the actual number, but you can imagine generally means 80% or so, right? 80% of people, when they got COVID, they did not have a horrible adverse reaction like they would have if they didn't get the vaccine. Mostly. So it's kind of it's percentages game. Mostly, generally. Those words, right? Almost always. Does this work out? Does this check out? All right? Any questions about what a qualifier is and why it's useful? You need it when you're arguing, right? You don't want to just say something and so this is always true when there are exceptions. If there are exceptions, you better soften your statement, right? So yeah, that's qualifiers. That's not horrible, right? If you want to say those kinds of things in logic, right, and be very, very extra precise and tell everybody about what you mean and have them all understand, then a quantifier is the right way to go. All right, so quantifiers are like a step up from qualifiers. They're like the logical version of them. So quantifiers are part of logic, all right? And we love logic, right? We know all the symbols. We got and, we got or, we got not, we got other things. Remember all those? So quantifiers are more of those things. More little mathematical symbols that make sure that everybody understands. So it's part of math, right? So it's time for some more math. Math time. That's where we're going, all right? That's the last part of today. So we'll spend some time on quantifiers now. The idea is, okay, I said something in English, it was a qualified statement. How do I put that into math? Because we know, cream or sugar example, right? English is very ambiguous, even when you have these qualifiers and you're trying to, make a precise statement. So how do we translate qualified sentences into math so we can prove them or disprove them beyond a shadow of a doubt? That's where we're going, right? So I'm going to teach you two quantifiers in this class. It's not the only two, but it's the two that people generally learn first. There's plenty more where this came from if you get to grad school or something. But here are two quantifiers, right? There are these symbols right here, right? Try to get used to them. And most of the qualifiers that we talked about in the previous section, you can use these two, some combination of these quantifiers and ands and ors and nots and things, plus the help of these guys, to get a qualified statement into a quantified logical precise statement, right? So this is the idea. So this is the first symbol. I'll teach you how to use it in a second, but just understand it when you see it. This right here means for all. It's just like you see it, you translate it into the words, the phrase for all. Okay? It is just an upside down A. The A did a 180. Okay? That's the idea. It's like it flipped around. That means for all when you see it. And then this one, same idea with an E, right? There's an E that did a 180. It means there exists. All right? So you see this symbol, you read it as for all. You see this symbol, you read it as there exists. Okay? So it's got the A and it's got the E, so it's useful. And there are plenty others, right? There exist other quantifiers that talk about things that these don't like cover, like things about time. That's kind of the next stage of like learning about quantifiers. Like, all right, this might not be true now, but it'll be true in 30 minutes. Like you can express that in math with other kinds of quantifiers. So it's called temporal logic. It's cool to think about, but that's like graduate level computer science and math. That's not as useful for us right now. So we're just going to learn these in this class, all right? But yeah, just like whenever you see this, for all, whenever you see this, there exists. And every time you use one of these, there needs to be a variable, all right? Every time you see a quantifier, it will appear next to a variable. That probably doesn't make a lot of sense right now, but it's going to act on that variable. All right, you're going to see a variable next to every quantifier when we use one. It's going to act on it. Okay, so here's some examples. Here's some examples of for all and there exists. Let's do one of each. So here's an idea, right? First of all, when we're making these statements, right, we're translating these sentences into math so we can prove them or disprove them. A quantified statement is just like this, like not X or Y or something. It's just like a normal logical statement. This is not a quantified. That's just a proposition, right? This is not true or false yet, right? It's like we're not sure what it is. It's something that we could prove or disprove. Yes? It's like this statement is a quantified statement. It's not immediately obvious that it's true or false. It's just an idea that you could prove false or could prove true, right? It depends a lot of times on a variable that's involved, right? So here's an example of using for all, like every value of this X variable is greater than 5. That's an idea that you could prove. Depends on the X, right, if it's true or not, but that's an idea that can turn into a use of a for all. You kind of see it? The for all is the every part. So here's how you write it. Here's how you translate this into math. And with enough examples, I promise you'll get it, right? Here's how you say it. For all X, okay, put a comma after that. For all X, X is greater than 5, right? And you kind of read it like that. Like for all X, X is greater than 5. But you think about it in terms of like plugging in values for X. Like for every value that X could take on, this is true about that value. Does that kind of make sense? It's talking about a million things at once. An infinite amount of values that could be plugged into X. And if you're claiming that this is true, then no matter what X could be, it's greater than 5. Does that make sense? That's kind of what that means. Right? Every value of X is greater than 5. For all X's, X is greater than 5. That's how you read that. That's how you understand it. And so this is not true or false yet. It's something that you prove to be true or false. Because like you need to show, right? If you claim that this is true, you need to show that like X could be 7 or something. X could be bigger than that. You need to show that X cannot be 2, right? You want to make sure that can never happen, right? Because if X is equal to 2, that disproves this, right? It would be false at that point. It's not true that every X is greater than 5. See it? You need to make sure that it works out. It's like that doesn't work out. So you need to make sure that it's not 2 ever. Stuff like that. All right? Are there any questions about that English turning into that idea? Does it make enough sense for now? For the first example? Because it is weird looking. I promise it'll make more sense with more examples, but I do want to make sure it doesn't look too weird. All right, if we're okay, let's have an example of there exists. Again, it's going to be appear next to a variable. It's always talking about variables, applying to a variable, right? So there exists a number n that is both prime and even. So yeah, that's something that you could want to prove. It is true, right? But it's just a statement. It's something that you have to go then and prove, but it's something you can precisely write down and everybody could understand, right? There exists a number, call it n, that is both prime and even. So here's how you say it. There exists, backwards e, there exists an n, and then the comma you usually read, like you can either pause there or you can say the word such that. There exists an n such that this is true about that n. That's kind of how you'll hear it said a lot in math. It's So there exists an n that is both prime and even, and so let's say this about, so there exists an n such that, what is true about that n? N is prime, n is prime, I'll just write this in English, and n is even, right? There. You can imagine that you can turn these into actual logic eventually with enough things, with enough ideas. You'll have to use quantifiers for that actually, but does that kind of make sense what's happening there? There exists an n such that n is prime and n is even. Do you see how this English above translates into this quantified statement in logic that you can then go prove or disprove? Any questions about that? Can you see the process? It's always next to a variable. It's saying something about that variable. There exists a value that I can shove into n, and here's what's true about that. For every value, for every x that I could ever choose, this is true about that x. It's talking about that variable, it's applying to it. Okay? That's what's going on there. And so, like, if you wanted to prove this, you'd have to show, like, give me one good value, right? You're just showing that there's one. There exists somebody. There exists an n that is both prime and even. You got to make sure, like, you can't prove it for n, right? If n is 7, that's wrong, right? It's prime, but it's not even, yeah. But maybe your only choice, right, is n equals 2. That would check out. You could use 2. 2 is the one. 2 is the one that exists secretly, right? 2 is prime, 2 is even. So n could have been 2, and that's why this statement is true. Does that make sense? So that is a true statement. But it's something you have to then go and prove and disprove. Okay? Any questions about that? Does it make enough sense? Oh, wow. I didn't think it was going to rain that badly. Cool. I will need different shoes. If we are happy enough, let's see here. I would like to ask you a question. All right? You can, let's see. I don't know. Let's go to the written nice page. I think that would be useful. So I'll stop attendance after we do this, but please humor me. Let's go to the written nice page, and I definitely want you guys to get in groups and talk about this. But here's my question for you. All right? You don't have to use quantifiers. Don't worry. I'm not even going to put those on the slide right now. I want you to just use English, because the idea is you need some English first to translate it into something that's quantified anyway. So what I'd like you to do is to try to specify what it means to be sorted precisely, right? Just in English. So I want a paragraph from you and your group, please. Specify what it means for like a bunch of numbers to be sorted. All right? What does that mean? What does it mean for a list of numbers to be sorted? Like here, I give you a Python list. These things. Why is this list sorted? You know just intuitively because you've been in enough math classes, but like try to precisely specify, like pretend that I've been hit on the head and I have no clue what it means to be sorted anymore. Okay? How would you describe it to me? How would you be precise? Right? Just pretend like you're talking to somebody with amnesia, and then we will take your ideas and we'll translate it to use of quantifiers. It's like, what does it mean? Like, how do you translate this idea? L is sorted. How do you be more precise, right? Than just saying that. What is the definition? How precise can you be, right? So, does the question make sense? With as much detail as possible, write down what it means to be sorted, and then we'll start thinking about quantifying that statement, right? And qualifying it. Yeah, give that a try. Give you a few minutes to write something down, and then we'll see what you're thinking. A lot of us will have the same ideas, because, I mean, sortedness is sortedness, right? But how would you describe it? Why is that unsorted? Why are not? Oh, and please do attendance if you've not yet done attendance. I'll stop that after this is done too. Good ideas. Do you stock think of examples of sorted things and not sorted things? Another couple minutes to get your thoughts in there. All right, my timer's about to expire. Was that enough time to get something in? Give you another 30 seconds to finish your thought and press submit. More closely. All right, let's see. Let's see. A lot of us probably came up with the same ideas because, like, we think of sortedness in the same way. But let's see. Let's see what words we chose because a lot of us probably chose similar words. And oh man, I did not bring an umbrella. All right. So, all right. What are we thinking? To be sorted means it's organized based on qualities. Okay, biggest to small. Good. So those are the words, right? Biggest to smallest. So it doesn't have to be ascending order. It could be descending like that. By color, alphabetical order. Good. Yeah. So that's a bit more generic, and that's even better than I was thinking. So that's a good idea. All right. For a list of numbers to be sorted, it has to be organized in a specific way. It's just that the first number, nice use of such that, I appreciate that. First number is one of a certain extremes, like either the biggest or the smallest. Last one is the opposite. And then everything else is in between. Good, yeah, so if it's not sorted, there's no logic behind the order. So yeah, there's a concept of ascending, descending. We're trying to get at those words, right? Previous number is always less than the following number. That's a good way of explaining it. That's simple, right? Previous number is always less than the following number. Because like you can just look at them, do they line up closely? Like that could turn into an algorithm for checking things. That would be useful for proving things, yeah? So I like that answer a lot. Good, short and sweet. And then one last one we see. L is sorted because the order of the numbers are from least to greatest. So yeah, those words, least to greatest. What does that mean? They're numbered from the lowest number all the way to the highest number. So it's kind of, you're implying this idea, right? Again, previous number is always less than the following number, or the following number is always bigger than the previous number, yeah? Interesting. I like that. So hopefully we see it. Are there any questions about these ideas? So like we want to be precise. That's how you could define it. And then eventually we want to turn it into math, just like to show beyond a shadow of a doubt. Like what could I prove to show that, to show that a list is sorted. All right, a list of numbers, list of characters even, if you want to think about alphabetical order. But here's kind of the idea, all right? So what does it mean that a list of numbers is sorted? A lot of us kind of came up with the idea that, like, all right, you notice that kind of this was happening, right? Boop, those were the numbers. You can think about it that way. Remember, at least ascending words. Like every element is every element is getting bigger. That's what you could say. Every element is getting bigger. Does that kind of make sense? And so if you wanted to prove this, you have to think about like what does that mean? So it's like, I know what mathematical symbols could you use now? It's like, all right, I could use less thans. That's less than that, is less than that, it's less than that, it's less than that. Because yeah, if you proved all those things, like, oh yeah, it's sorted. So we're getting closer and closer to like more precision. That's how you do it. Though, if you stare at it long enough, you can imagine this list is sorted, sure, but what about this list? L prime, 1, 2, 2, 2, 2, 3, 3, 4, 5. Is this list sorted? I think it is, right? So it's not just this. It could also be that, right? It could stay the same spot for a while as long as it doesn't like fall down. So I think a better idea is that, yes, every element's getting bigger or staying the same. See how it's more precise now? So you got to think about this stuff. If you want to prove, if you want to write down, if you want to be a mathematician, you have to write down exactly what it means for something to be sorted. All right? That's just one of many things for you to do. So, all right, this idea now. I like the idea of using these less thans. Like, do you see how, like, if all of these check out, if that's true about those guys, and that's true about those guys, and that's true about those guys, and that's true about those guys, they kind of chain together, and they prove that it's all sorted. Yes? If I could do that less than or equal to calculation on every little pair of things, one after the other, then if that's true for all of them, it will be sorted. You see how we're kind of handing off the problem to the less than or equal to sign? That's good. That's very good for us. All right? That's kind of what I want to do. And so, all right, it's useful, as a computer scientist at least, it's useful to think about, like, how would I write a program to, like, go and check that a list was actually sorted? Because, like, that'll turn into math. That'll turn into a statement eventually. Like, it's useful to have the computer science knowledge, I think, even if you want to be a mathematician. So, like, how would I take this list and, like, in code, go and check this is true about these guys, right? That checks out, because, like, Python can do the less than or equal to check, right? It's just like, what do I put there? What do I put there? How do I get this out? How do I get this out? Kind of thing. I can use the indices, can't I? Remember that? Be like, all right, go to L at index 0. That'll get me the 8, yeah? Make sure it's less than or equal to L of 1. Do you see how that check, you can't write it like that. It's got to be less than sign equal to sign. You see how if you checked that, it would give back true for that one? We just want it to be true for all those pairs of indices. Does that make sense? That can turn into math. That is very powerful. It's a cool idea, right? We want that to be true. We want this to be true, right? We can use mathematical symbols because we're talking about math, like less than or equal to, right? L of 2, like we want that because that would pick out those guys. Index 1, index 2, because it starts at 0, right? And so if you think about it, I want this to be true because quantifiers involve variables. Like there's a leap that you need to make here, but I'm getting you to make it slowly but surely. I want this to be true for every index, right? Like we're like, this one's the one before, this one's the one after, this one's the one before, this one's the one after. I want that to be true for every possible index that applies to this list, yes? Only if I have all of those less than or equal to's do I know that the list was sorted. Well, here's how you would do that, right? You'd loop over them, right? In a program, be like, all right, go to L at I, make sure it's less than L at I plus 1, less than or equal to L at I plus, because that's the one after it. Does that make sense? Have I be 0, right? If I was 0, that would give you that one. If I equals 0, that would give you this comparison. If I is equal to 1, that would give you this comparison, right? That takes a lot of thought to get to that idea. But like, do you see now that I'm giving you that idea, that thought? Do you see how it works? If I did that, and I used every I that applied to this particular list, didn't go too big, didn't go too small, started at 0, 1, 2, 3, right? Because it compares I equals 3, index 3 to 3 plus 1, 4. That's the last one. If I did all of these checks for every possible I, do you see that it would work? And it would tell me that it's sorted? And I just did a key word, didn't I? Here's what it would be in math then. For every I that checks out, make sure this is true. Do you see it? That is a mathematical definition of sortedness. It's interesting, right? I hope you agree. I like this. That's cool, right? For every I, right? For every I that works for the list, that applies, right? You have some side conditions, I guess. But like, make sure this is true for every I. Make sure it's true for I equals 0, because that would prove that these two are less than or equal to. Make sure it works for I being 1, because that would prove that these two are less than or equal to. All the way up to I being 3, right? For every I that applies to this list, check this out. If that is a true statement for all those I's, then the whole thing, right? This final quantified statement is true, which means the list was sorted. Does that make sense? That is a definition of sortedness. And so if you want to translate it back into English, like more precise English now, it's like for every index I that makes sense for L, for every I, right? For all I's that makes sense for L, here's what should be true about that I. Here's how I want to use the I. L's element at that index better be less than or equal to L's index, L's element at the one right after, at index I plus 1. So we're just using math. We're going into lists, right? Using math to get over to the next index. We're using less than or equal to because we know what that means in math. And we're using a quantifier. We need the quantifier to try it for everybody because that's for all. So that, I think, is the full story. Does that make enough sense? Maybe you weren't going to discover that yourself unless I told you, but do you see it now? Any questions about that? That is the power, right? That's why you need these. That's why you're learning them. So, all right. You guys will be way ahead if you need to. If you're ever going to be a math major, you'll know this way ahead of other people. And then also computer science majors need this idea too. So you'll learn about this in CSCI 26, some more advanced computer science class. So you guys are going to be very ahead if you take those. So, all right. That's this one. I have one last example now that you kind of get the idea. All right. Now that you get the idea, let's go back to the written ice page. No, let's not go to the written ice. You can write it down wherever you want, but I want you to discuss at least, because it's hard to write the symbols. Let's not worry about writing it down, but I want you to discuss at least. Here's what I want you to discuss with the people sitting around you. Try to make a statement that involves the use of quantifiers. Here are your quantifiers for all, and there exists, right? And here's our solution from last time. For all i's, L of I is less than or equal to L of I plus 1. That was our solution for the last problem. I would like you to, using these ideas, right, using my examples, try to extrapolate. Try to make a statement that uses quantifiers that talks about the following, that represents the idea of this. Every non-empty list of numbers has a minimum value in it. That is a true statement, but I want you to be able to specify it, all right? Every non-empty list of numbers has a minimum inside of it. Like if I gave you this list, 3, 1, 2, no matter the order, right? You're always going to know that there's a minimum somewhere. Maybe it's duplicated, but that's fine. There's a minimum somewhere. Even a single valued list, right? Just the one value is the minimum. The only time this doesn't work is if it's empty, so we have to say every non-empty list of numbers. But that's a true idea, right? Can you precisely specify that idea in math? So like take it, write in English first, but try to figure this out, right? Maybe start with English and convert it to math if you need to. But how would you specify, like, first of all, you need to talk about what minimum means even, right? How would you say this? Do your best to try to translate this idea into math that's going to use at least one quantifier, okay? So give that a try. Discuss with the people sitting around you. See if you can find it. You can find the idea, and then we'll talk about the answer. You don't have to write this down, though. Just want you to discuss. It is a true statement, but we're going to be able to prove it. I want to write it down. Every non-empty list of numbers has a number. Some of those words kind of sound like for all of there exists, right? Multiple pieces. Even if you keep it in English, though, try to make it more and more precise. Stuck with the quantifiers. Try to make it the most precise English you can, at least. Another minute to discuss. Then we'll see if anybody's brave enough to share their idea. Be as precise as you can be. You never had to worry about what minimum means, have you? Alright, that's my timer. I think that was enough time. So, any brave souls want to tell me, like, what they thought? Like, were able to come up with a coherent answer? And can you say it back to me in English? Or are we all shy? If nothing else, some of these words are key words in this statement, right? I think some of them will turn very easily into a quantifier. Do you agree? What's one of those words that probably could turn into a quantifier? Every, for sure. Yeah. Every. Does everybody see the word every kind of is screaming for all? That will turn into a for all when you make it precise, yeah? Maybe we did that, but we're shy to say. There's also one more. There's one more, really a phrase in this sentence. So after every, from here onwards, is there another phrase or word that kind of screams that there should be a quantifier there? This one might be more subtle. And where could it apply? Non-empty, that doesn't really sound like everybody there exists, right? Or I guess technically if you want to get precise, like, all right, there exists at least an element if it's non-empty, yeah? Technically that would work out. But just like synonym-wise, does everybody see that has a, for sure, now that I pointed it out, is kind of screaming there exists, right? It's kind of a synonym. Same phrase. There exists, there is a minimum. It has a minimum, yes? So if nothing else, we're going to see a for all and a there exists at least once each in our final answer, yes? All right. So with that in mind, let's work our way towards perfect math, all right? So we noticed a few things. So the very first step is every time you use a quantifier, you better be using a variable because it kind of applies to a variable, kind of introduces a variable. It's like a way to create one in math. So we have to introduce a variable to talk about things that we want to talk about. So for example, we say every non-empty list of numbers has a minimum. We better give a name for that list that we're trying to talk about, even though it's a variable, right? Could be any list that we're talking about. So it's like we're applying to every list. For every list, this is true about every list. Does that kind of make sense? So like instead of saying every non-empty list of numbers, just start saying this. Be more precise. For all lists L, yeah, give it a name. Now we can talk about it. We can talk about its indices, talk about its size. This is more precise than this, but it's the same meaning. All right. Every non-empty list of numbers has a minimum. For all lists L, if L isn't empty, then there exists a minimum value in L. Does everybody see how that's the same idea? But now it's looking a little bit more like logic. So like we got the for all, we got the there exists in there, we did those translations. And then this is also saying that it's not empty, right? Every non-empty list of numbers has a minimum. Another way of saying that is like if it's not empty, then there's a minimum. Yeah? And that is another logical symbol, isn't it? Our if-then statements in math turn into, it's called implication, right? The arrow. Remember that? So we're getting closer and closer to symbols. Yeah? That's the goal. It's like, all right, for all lists L, if L isn't empty, then there exists a minimum value in L. And then, like, you can use the length or something, check if it's 0, stuff like that. Like, you got a len function that you could use, that's fine. So really, the last bit of work is the idea of there being a minimum, right? Because minimum is just a word in English. How do you specify that something's the minimum value? Just like we've specified sortedness, you're probably going to need to use the word less than, right? Or less than or equal to. Because that's what it means to be a minimum, right? What does it mean to be a minimum? It's a philosophical question, or just a mathematical question. Because, like, that's a piece of this puzzle, right? If I was able to specify what it means, beyond a shadow of a doubt, for something to be a minimum, then I need to use it here, right? That's part of this. So we need to be able to describe the idea of there being a minimum in just math, right? That's the goal. It's a little philosophical and also mathematical at the same time. I like it for that reason. So what does it mean for something to be a minimum? Like if I give you a bunch of numbers and tell you that 1, like if I give you these 3 1 2s, like why is 1 the minimum? Because it's less than everybody else, yeah? Or even if there were some other 1s, like why is 1 still the minimum now? Because it's less than or equal to everything else, yeah? It's the smallest thing, for sure, even if there are duplicates. So that's the idea. It's less than every other number in the list. That's what it means to be the minimum. Do we agree? Does that make sense? That's what it means for there to be a minimum. Like we've never thought about that before. Now we know. It's less than every other number in the list. And then we want to translate this idea now to math because it's part of our answer. It's less than every other number, so you see that there's going to be another for all. That makes sense? All right, go and try. For every other index, go and try that index and make sure, right, that it's less than or equal to the thing that I'm looking at and calling the minimum. Yeah? That's what we got to do. That's what we got to do. So again, like once you have quantifiers, the secret is there's always going to be a variable that pops up. We need some more variables to talk about, like where is that minimum? What's the index of it? What are the indices that we're talking about for every other number, right? So every time you have a quantifier, there will be a variable involved, but we will get there slowly but surely, all right? And so with that, here's the answer, all right? Let's translate this as much as possible, and then we'll get to the minimum idea. So for all lists L, that one's quick, right? For all lists L, comma, here's what I want to say about L. For each list L. If L isn't empty, then there exists a minimum value, right? So it's an if-then statement. If L isn't empty, then this is true. It looks like this, right? It's something implies something else. It's implication. If-then, logical if-then. So if L isn't empty, how can we say that in math? You can say it with len, right? If the len of L is greater than 0, kind of use Python and math together. That'll work. So if this is true, then, right? And this is the then part. So if L isn't empty, then there exists a minimum value in L, okay? And so like we need to say this, right? We need to say this part. There exists a minimum value in L right now. That's the last piece of the puzzle. We just say it precisely with math. So what we'll do is we'll use the index, right? We'll use the index because that will be where the minimum is. Like there exists a minimum value. You can use that. We can say that in terms of its index. Let's say that there exists a minimum index, an index of the minimum. Say IDX. There exists a min index. That's like a variable. That's where it is. Somewhere in the list. Could be the start. Could be the end. It could be anywhere. But it's there. I promise. There exists an index of our minimum such that it is a minimum index. All right? I want to talk about why it's a minimum now. It's less than every other number. So there exists a minimum index, and it's a minimum because for every index that you could ever want to go to, including the one you're at, that's fine. For every index I that makes sense for the list, here's what's true about the thing at min index and the thing about I. The thing at the min index is less than or equal to every other thing. L of I. I guess this is too far over. There. Does that make sense? So if for all lists L, if the length of L is greater than 0, if it's not empty, then there exists a minimum index such that this is true about that index. For every other index, for every index I, compare that thing at that index with the I, it's always less than or equal to. This always checks out. That's what we're saying. Does that make sense? Why that's saying for every non-empty list of numbers has a minimum? You see the progression of it all? If you want to do math, you got to be very precise. And now we can prove or disprove that. And that is a true statement. There are ways to prove that, but that's beyond the scope of this class, though. All right? So if you want to go back to math, or you want to go back to English, sorry, from the math, like here's the precise English that describes this. All right, for all lists L, if the length of L is greater than 0, that means that it's not empty, then here's what's true about that list L. Then there is an index in L that we'll call min index, such that here's what's true about that min index now. For every other index I, or just including the one itself, that's fine, it's less than or equal to, for every index I in L, here's what's true about min index versus I. You got one index where the minimum lives, and every other index is, we'll call it I, have a chance at being I, range over the entire list, like a loop over the list, right? That's what the for all is doing. The min index always is the smaller thing, smaller or equal to thing. That's what it means to be a minimum. Does that make enough sense? It is a lot of new ideas, a lot of new symbols at once. It's a more complicated lecture, for sure, more complicated section of the lecture. But I hope you see that it's useful and that with enough examples, you will get it too. Okay? So I'll have some more examples of this next time. That's where I want to stop for the lecture part. But I do want to release your next essay. You got one due? You got the big one due this week, right? So this will be a smaller one. Do let me know if you're having any questions about the one that's about to be due, because that is an important one. I want to make sure you're getting it. But this one will be nice and easy after a longer one. So it's going to be a 750-word essay, so less than the one that's out, but a decent amount of work still. So it'll be a two-week essay. 750 words, and here is your prompt. All right. I would just like, it's a more philosophical idea. All right. So what I want you to do is think about digital art. All right. So here's your prompt. Go find your favorite painting. Pick your favorite painting, or go and find one if you don't have one yet. You need to be a patron of the arts, right? Go pick your favorite painting that was made sometime before 1900. So 1899 and earlier, right? Go find a painting from that era. Go to Renaissance, go to like, even the 1800s is fine, even, but no later than 1899, right? Go find a painting that was made sometime before then that you like, right? Your favorite painting of all time up before 1900, right? And then I want you to pretend that the artist who made that beautiful painting that you like so much was alive today, and they made that painting digitally on a computer using like a tablet like I'm doing when I draw on the screen. They use like a drawing tablet or like a screen tablet, and they used Photoshop and a bunch of digital brushes and stuff like that. It was all virtual. They still made paint strokes technically, but it was virtual paint, all right? Does the setup make sense? Pretend that was all happening, all right? And my question for you is, would that painting now be as beautiful to you or not? Would you think that it's still beautiful, even though it was made digitally and it wasn't made on canvas anymore? Why or why not? And so I just want you to build on top of that, analyze your ideas, talk about what you're thinking. So very open-ended, all right? And I want a 750-word essay about it with the one requirement that you cite at least one thing, all right? So go find an article on the internet about this idea and have at least one citation in your essay and a works cited page with that one thing. You have more things if you want. I got 5 minutes, guys. Do that, and then here are some useful things that you could think about reading. So here are some potential articles that you may find helpful to cite. You can find your own if you'd like. And yeah, so does the setup of the idea of the essay make sense to us? So go find a beautiful painting that was made a long time ago. Pretend it was made digitally. Would it still be beautiful? All right, that's your question. And if you're not sure about like what you can do digitally, here are some people that I follow on Instagram. Here's like a person that the first one is a person that likes to draw very like cartoony, and like here's more of a realist kind of artist that's still doing it all digitally. Do I get to see things like here's pretty things made by this person? I guess you'll have to scroll or you'll have to like make an account. And then here's another artist. This is more like realism. This is the kind of thing you can do. It looks like it's made on canvas, but it's not, all right? So feel free to use that as ideas. But I think that's everything that I wanted to say. This will be due in 2 weeks. Watch the due date. We're good? All right, then I'm good. That's all I got.